Hello and welcome to part 2 of lecture 25, where we're going to continue to talk about static equilibrium. In this second video, I'm just going to go over a few examples to show you some more variation of the problems you can see. So we're going to start with example 1 because this is a system with a non-uniform density object, in this case a rod. So that's kind of another type of problem you could see. So in this case, I give you a rod, I give you its exact length in meters. I tell you that it has a linear density that varies with length linearly, which is repetitive. But anyway, so it starts with some baseline density at the left side, and then by the time you get to the right side, it's twice as dense. The density has doubled. Okay, and that baseline density is 2,200 kilograms per cubic meter. All right, so that's the our density here, our volumetric density. All right, and really, I suppose, actually, let me clarify that, because really, since I'm doing everything over one dimension, I'm not actually interested I don't care how wide the rod is. I don't care what its cross-sectional area is, for example. So I'm going to give you the density in kilograms per meter, because that's what I'm integrating over. So just clarification there. All right. But anyway, so I have the solution written out here. I just want to quickly go over it. So this is a linear density we've seen before. It's kind of a system that I like to deal with. So we already know from a previous example that through integration, we can find the center of mass to be 5/9 L, which in this case is 1.34 meters. So it's out there, right? It's actually not quite that dramatic, but it's not at the geometric center. It's further towards the denser end. And we can also find the total mass by integrating, and that gives us this value here, right? This is kind of the functional form of the total mass. And in this case, since L is a known value and lambda naught is a known value, and that's different from previous problems where we were just interested in, say, the angular acceleration of the system. In that case, it was independent of both mass and L. It would apply to any rod that had that density distribution. But here, since we're dealing with values, we're interested in specific magnitudes of forces and torques, we need a definite length and a definite mass if we want our answer to have units of newtons, for example. Okay, so anyway, so we get a mass of 6,765. All right, looks good. All right, so to solve this problem, we're going to use sum of forces on the y direction and sum of torques about our pivot. We don't have to care about anything in the x direction because there are no forces in the x direction. All right, and essentially the idea here is that we're going to has a hook where mass can be attached to the far end. How much mass must we add to the hook to put the system in static equilibrium? So the idea here is that it's kind of nailed to the wall or something, right? It's attached at some point right there. That's also going to be our choice of pivot. And if we just attached it at its middle, right? Because I say that here, that a rope has been tied 1 meter from its left end that supports the rod. So actually, I shouldn't say that. The pivot is not exactly in the geometric center either. The pivot is actually where the rope is, right? That's where the tension force is. But by choosing my calculated pivot to be there, my tension force is not going to show up in my calculated torques. But the idea is, anyway, we've attached a string. It's kind of in the center, but not quite in the center. And if we just attach that string, the offset center of mass would cause the system to start to spin. It would start to spin in the clockwise direction, so the negative direction. But if we balance it out by attaching a little bit of hook to this end with some mass on it, then that, of course, will prevent the system from spinning. Okay, so that's what we're going to do. All right, so then, again, I'm only interested in the y direction. So in the y direction, I've got gravitational force, that's this one, pointing down. I've got the attached mass. All right, I suppose this is the mg, little m for the attached mass of the hook, and then the mass of the rod, big M times g. Okay, and their location doesn't matter because we're just dealing with forces, not torques. And then I got the tension pointing up. Okay, my sum of torques about my chosen pivot, again right there, is just going to be the hook mass times gravity times the distance from the hook mass to the pivot. And you can see here that the moment arm is clearly the full length because everything's perpendicular. And then this is the much shorter moment arm to the mass of the rod and gravity, and then times the length from the pivot to that location, which ends up being 0.34, because 5/9 of 2.05 is 1.34. Oh, okay, 1.34 minus 1 is 0.34, okay? So we can use our torque equation to solve for the mass of the hook. It ends up being 2,300 kilograms, okay? Big hook, all right? And then in part B, I asked what is the tension in the rope. Well, since I was able to use the torque equation entirely to answer part A, I can then actually just use the force equation to solve for tension. And I need the M, right? So I had to have found M using the sum of torques, and then I'm going to plug that into my sum of forces in Y. But once I have both masses, the hook mass and the rod mass, then the tension force is just enough to balance them out. So just multiply it by G, and so there we get 89,000 or 88,000.9 as our force of tension. All right, because everything's very large and massive here for whatever reason. Okay, so there you have it. It's the idea here is that if this was, say, some other linear density, you may have to actually do the calculus and remind yourself how to find the center of mass, find the total mass. You don't care about the moment of inertia here, because the moment of inertia I would only show up if the system was accelerating. But since it's not, since it's equilibrium, you would never need the moment of inertia. You could find it, but it wouldn't be relevant to this particular problem. Okay, so there's another example. Let's take a look. I'm leaving these questions for you. You can answer them. Example 4 and example 5 are similar enough. I want to leave them for practice. I included the solution to example 6 because this is a case where the torques don't end up showing up. They just end up zeroing out if we make a good choice of pivot. And so here's the system. So a 240 Newton weight is hung from 2 ropes as shown, right? So one rope is entirely horizontal, the other rope is angled. What is the tension force of the horizontal rope? Okay, and that's what is its magnitude? Little typo there, bad wording. So then I write my sum of forces. Okay, so I got my sum of forces in the x direction. I've got FTRx because it has an x component, right? The FTR for right. So that force has 2 components, a x component and a y component. So the x component is FTRx minus FTL because the horizontal rope is pointing entirely in the negative x direction. And then I got the y component of the right hand tension force minus 240. Oh yeah, because that's the force of gravity pointing down. Okay. And then if I look at what's going on in the y direction, I got FTR, already said that, excuse me. And so then my torque net pivot, I say is 0. Well, how do I know that? Well, I choose this to be my pivot. All of my forces actually act right there. So I'll draw my last force just to be clear on this, that this right here is my FG. Okay, this is my final force right there. That's it. Right? Those are the 3 forces. They all are applied at that location, at the knot. And so if I choose that as a pivot, all of them have a moment arm of magnitude 0. The length is 0. So then the torques have to be 0. Okay. And so then I go ahead and I want to solve for FTL. Well, if I look, the FTL shows up in this equation, but I don't know FTR, let alone the x component of FTR. So I got to do a little bit of work here. So the first thing I would do is I'll solve for the vertical component or the y component of the right hand tension force. So I'll use sum of forces in the y direction to do that. So then FTR will just be the weight divided by sine 30 because the vertical component would be sine of 30. So you can see because the right hand triangle here with the angle that we're given looks like that. So I end up with 480 newtons. All right, looks good. So that is the entire hypotenuse or magnitude of FTR. And then if I think about it, well, FTL is just going to be equal to the horizontal component of FTR. So if I know the hypotenuse, I can just find one component with a triangle. And of course, that is just going to be 480, the hypotenuse, divided by cosine of 30, because that'll just give me the horizontal component, which is actually exactly what, of course, F net x, would give us. So 416 newtons is this force right there. All right, very cool. And it's really neat to think about that it's so much larger than the 240 newtons of gravity. Because really, in a sense, isn't that the only external force I'm applying here? Well, yeah, but the fact that the ropes are mostly horizontal means that they end up requiring more and more tension. For example, if I had FTR at an even less steep angle, let's say if I had it like 10 degrees, well, in that case, both FTR and FTL are going to be way bigger. Okay, that's kind of interesting to think about, isn't it? So down to the less slack there is in the system, the greater the tensions. Sounds intuitive, though. Okay, so I included one more. It's kind of similar. It's going to be a sum of torques being 0. I included this example because I wanted to show that we could work with things that aren't just rods and cords. We can do things like spherical objects, like here. So a 600 Newton ball shown is suspended on a string, and it rests against a frictionless vertical wall. The string makes an angle of 30 degrees with the wall. What is the magnitude of the tension force of the string? So here I can also choose a pivot where all the torques go to 0, not because all the forces are acting there, but because they all act parallel to the moment arm. Because if I think about, okay, let's think about the forces, right? So first of all, if I choose the center of mass of the ball as my pivot point, well, gravity acts at that point, so it has a moment arm of 0. There'd also be a normal force acting on the ball through contact with the wall. That's going to point exactly in the horizontal direction. The moment arm is also exactly in the horizontal direction. So the angle between the two is 180 degrees. Sine of 180 is 0. So that means that, in other words, this force doesn't create any torque. That makes sense. It's not twisting it at all. Well, what about this tension force? Okay, same sort of thing. It's not creating any torque because the distance from the pivot is exactly along the radius of a distance of 1 radius, which is the same as here, right? That's the displacement in magnitude. But then the angle between the two are parallel. Okay, so no torque. Okay, so there's no torque created by the forces, but they still have values. They just don't create torque. So then I do a F net X, F net Y, and then I can just use entirely F net Y in order to solve for the tension. Okay, if I want to solve for the normal force, I would use F net X. Okay, so pretty straightforward, but just wanted to show the variation. The final example I want to show you is a very complex one, and one where I kind of break my rule of choosing the pivot to be the location with the fewest forces. Because in this particular case, it works out to get the algebra, which is rather complex. It actually works out to not do that. I wanted to prove to myself that I could choose that. If I choose the pivot here, it certainly does work, but it's a pain in the butt. And this is a particularly complex problem. It's really kind of pushing the limits of how we would solve it, especially by hand and maybe not using matrices. But we can. I have, obviously, the work shown here. So what's going on? So a ladder is lent against a wall. The coefficient of static friction, mu sub w, between the ladder and the wall, so w for wall, static, S for static, is 0.3. The coefficient of static friction between the ladder and the floor is 0.4, and that's SF. Okay? So what makes this problem complicated is the fact that there's friction between both the wall on the ladder and the floor on the ladder. Because 90% of the time when you see this ladder leaning against a wall problem, only one of the two surfaces, either the wall or the floor, has friction, and others assumed to be frictionless or really smooth, which is great for solving it, but it's not very realistic. In the real world, both surfaces would probably be pretty rough and would be helping the friction. And so this is the more realistic version, but it ends up being quite a bit more complicated because you're introducing many more unknowns. And then in this case, at least I have a uniform density rod, so the center of mass is in the middle, a uniform density ladder. But then what I'm asking for is not even a force, but instead for the angle, which inherently can be a trickier thing to ask for. So I was asking what is the minimum angle that the ladder can form with the floor and not slip. Okay, so here I've just drawn the free body diagram. You can look over that. I'll be posting as notes with all the relevant angles and displacement vectors and so on. Obviously the forces were already printed on there in blue. So here's the setup for all equilibrium problems is to write the sum of forces and sum of torques. I think we know that by now. All right, so here we got our sums. Okay, so what's going on, right? Well, we got some forces. We've got FW, that is the contact force with the wall, right? That's like normal force with the wall. FFF, that's the friction from the floor, so friction floor. And then I've got, in the y direction, friction wall, because that one points up. And then the force of, this is the normal force from the floor. So F here doesn't represent friction, but it's floor. So it's a force from the floor. And then I've got FG, which isn't, right? So that's kind of the odd one out, right? It's not a contact force and it's not friction. It's a non-contact force, okay? So there's my full sum of forces. Over here, what I'm writing, FW equals FFF, well, that's just showing that my result in the x direction or my setup in the x direction is so simple, I can kind of immediately come to that conclusion. So I want to just out the gate point out then, okay, well, we got that our two lonely horizontal forces must balance each other out. Meanwhile, our torques about my, oddly chosen pivot. And really, this is the only time I've ever seen a problem where it helped me personally to choose the pivot in the middle. Is I choose it about the center of mass, okay? And so in that case, I get all the contact forces and friction forces, no gravity, okay? And then I think about what each of them are. So here I'm just showing what each torque ends up being, okay? So as far as the sign of the torques, if we look here, because I'm taking a typical coordinate axis, we're choosing the counterclockwise direction to be positive. Well, if you look, the normal force from the floor wants to rotate in the positive direction, so that's torque F. The friction force, however, wants to rotate in the counterclockwise direction, the clockwise direction, which would be negative. And this, the normal force on the floor wants to go in the counterclockwise direction, the positive. The normal force from the wall wants to go in the clockwise direction. That's also going to be negative. And then actually the relative to our chosen pivot, the friction force from the wall also wants to rotate in the counterclockwise, or excuse me, the clockwise direction, which is negative. So actually 3 out of our 4 torques are negative. Okay, good, check that out. And so here I just go through and I kind of come up with what each of them are. In the interest of time, I'll just kind of quickly show that it's just a matter of sine and cosine of alpha, because it's all just going to be components. Essentially, it's all just based on these 2 triangles I drew, as you can see, pretty straightforward. All right. And so then I can go ahead and set up my torque equation like this. L will cancel. That cursive L just represents the half the length of the overall ladder. The total length is 2L, but I wanted my variable to be L for ease of solving. So then it simplifies to cosine alpha, normal, I have a lot of F's. So FF minus FFW, which is the normal force of the floor minus the friction force of the wall. That's all times cosine of alpha, and that's once I did all my components. And then on the right-hand side, because I'm going to add it to the other side, I got the sine of alpha, and then friction force of the floor, and then normal force of the wall. Okay. Then I'm going to do the substitution. I'm going to replace FW with FFF. Okay, so then this just becomes 2, as you can see. All right. And so then I'm going to continue to simplify here. I'm going to write some of my friction forces. So the friction force of the floor is the normal force times mu s times F. Okay, that's going to help me actually solve things. Meanwhile, the friction force of the wall is the normal force of the wall times the static coefficient between the ladder and the wall. All right, so I make those substitutions. Then I start canceling things out, because then my FF actually shows up in every single equation. Oh, great. Now I've actually canceled out my only unknown. And then I'm just going to do sine over cosine. So I'll just divide both sides by cosine, like so. Right? And then that's going to give me a tangent. Everything that's left is just this, because again, I cancel out my one unknown force by kind of simplifying and making it all be in terms of a single force, which of course the sum of forces allows us to do. And there you go. And that's a nice result. We should expect it to be a nice result. In other words, we should expect the angle to be dependent on the friction coefficients, both of them, and the overall shape, and that's all it is. Okay, and so then it ends up being 48 degrees. All right, and so anything, if alpha is any steeper than 48 degrees, so if I had the ladder instead like this, well, it would slip. It would slip because what would happen is the friction force with I guess in that case it would be with the wall could no longer support it. It would start no, it would be with the floor. All right, so it'd slip from the bottom side. All right, let's see. Or is that the side with more stability? We might have to test it out, because definitely if it's steeper, then it's definitely going to slip. Right, so if I make the angle less than 48 degrees, then it will slip. But I'm wondering if we make it steeper, actually, I think it continues to be stable. So our limiting criteria is, we shouldn't think of it as the maximum angle, we should think of it as the minimum angle. So I want to restate or correct myself. Okay, so alpha represents the minimum angle at which the ladder is stable. All right, cool. So, kind of upper limits of complexity,